In this session, I would like to talk about hashing. Hashing is a data structure generally which would like to do insertion, deletion and search effectively. They are called dictionary operations. Finally, I would like to implement dictionary. Okay. So far, we have seen some data structures. We'll see how they work for these operations. So linked list, if I take, what happens? So if I take linked list of data, then time complexity of search, we don't know where we are keeping a data, then we have to search entire thing, right? Two, if you have a nodes in the linked list, it takes order of n time for search, right? What about insertion? I can do at least insert in front, right? Then order of one time, better. Now deletion. For deletion, definitely we have to search for the value, correct? So if I search and delete, it takes order of n time because we don't know where is data. Now we'll see BST, binary search tree. In that binary search tree, so why I'm preferring binary search trees? In that binary search tree, you have ordered data, right? You are ordering the data, correct? If you have ordered data, probably I can do searching better, right? So in binary search tree, the time complexity will become order of h. But in the worst case, it will be, we know that, order of n, correct? In the worst case, where the height is n. But on average, in your binary search tree, there is a mathematical proof for it. On average case, the height of the binary search tree is log n. So what can I understand from this is, most of the times your binary search tree is having log n height. So safely we can assume that, so search takes only order of log n. But in the worst case, however, worst case is worst case. In the worst case, your tree will be skewed tree and it takes order of n, not an issue. Next, insert. What is the time complexity of insert in binary search tree? Order of h, but in the worst case, that would become order of n, right? Deletion also order of h, but sometimes it will become order of n. So let's have better thing, that's why. So we'll go for AVL tree. In AVL tree, the search takes order of h, but h is strictly log n, correct? So I can say that order of log n, and insertion order of log n, and deletion order of log n. At least it would be better than linked list and binary search tree, correct? But balancing we have to do, right? So sometimes balancing takes, of course, balancing also takes log n time, but that constant factor, because of that overhead, pointer, linkings and everything, so maybe it takes little bit more time than log n. I can say 2 log n, 3 log n, right? So leave it. Finally, these are all the data structures we have. Now we'll see hashing also. So hashing is also one of the data structure to implement dictionary, and it is specially designed for implementing dictionary. We will see that. So using hashing, our theoretical goal is implementing search, insertion, deletion in order of one time. So we will see whether we can achieve it or not. So first we start with basic hashing technique, that is direct addressing. Okay. So in direct addressing, what I do is, first I would know the range of the numbers you are going to insert. Example, the range of numbers you are going to insert, I know them, is 1 to 100. Then I will create an array of 1 to 100 directly. This is a range of numbers, I know them. So I create an array of 100. I assume that integers, let's say you are going to store from 1 to 100. That's why I take array from 1, 2, 3, so on up to 100. This is your array, let's say. Okay. So I assume that index starts with 1. So we can later update, adjust it to zeros, not a problem, right? That's why we learn how to use this array from 1 to 100. Then later we can adjust it to 0 to 99 based on our programming language which you are implementing this hashing. So let's say in direct addressing, for every data item I create one node like this, one memory location in the array. So now example, let's say 23 comma 34 comma 75 are the values you are going to insert in this array. What we do is, directly I go to, let's say the name of this array is hash. I will go to hash of 23 and I mark it. That means I make hash of 23 to 1. That's it. So if you insert 34, then directly go to hash of 34, make it 1. So if you do that, what happens? It will take only 1 unit of time to do that, correct? So this is the way insertion can be done in order of one time. Now we'll see search. Example, I would like to search 27, which is not available. We know that, correct? Let's initialize every value with null first. Okay. That means nothing, nothing, nothing. So if you do that, of course, so we can make it 0 also if you want, right? So if you initialize this entire array with zeros, then whenever you get the data, the correct, so every data item has a reserved position, right? go there and mark it. If you do that, so what is the time complex of search? How you search it? 27, go to hash of 27. If at all if we store 27, we stored it in only hash of 27. Directly go to hash of 27. If it is 1, it is available. That means it is there. Otherwise it is not there. Correct? So that's why time complexity of search will become order of 1. We'll go to delete. So what is the time complexity of deletion? How you delete it? Example, you want to delete 75. Search for 75. If it is there, then hash of 75 will become 1. Make it 0 and that's it. It is the deletion, right? So time complexity will be again order of 1. Easily we can understand because after all you did search, right? So search, insertion, deletion can be done in order of 1, order of 1, order of 1 time. But the limitation is you should know the range of numbers. One thing. Second one, sometimes what happens, your range will be very huge. Like what if your range is very large, like 1 to 500 crores. See. But the numbers you are going to store at any time are 5 or 10. The range is different, but the numbers you are going to store are only 5 to 10. Then what you have to do in this implementation? We have to create an array of 1 to 500 crores. So if you implement that kind of thing, it will be definitely inefficient, correct? So you, for creating a space of 500 crores, probably you consume all your memory. So that's one serious drawback. And one more thing, are you using it? No, you are not using it. You have only 5 to 10 integers to be stored. So that's a problem. Range is very high, but we have only few numbers to insert. That's a problem with direct addressing. So it won't work. What to do then? We have another model, that is, mapping. That means rather than directly creating an array for total range, we do small modification. That is, so this is, let's say, your range. Okay, very huge. But what I do is, I know that the range of numbers are like, the numbers I'm going to insert are, let's say, something 20 or 30. If I know that, I create only array of 20 to 30. Let's say this is array of 30. This is your range of numbers, 500 crores. Sir, then how you map it? Here in this problem, you simply directly hash of 1 was going hash of 1, 100 was going to hash of 100 in that way. But what about here? So in this problem, what I do is, somehow I have to map all these range to suitable memory location. Correct? For that we use hash function. Okay, we'll see what is hash function. Example, let's say my range is something 1 to 50,000, but I know that at any time I am not going to store more than 50 numbers. Okay, so otherwise, for easy discussion, I assume that, let's say, I am going to store at most 13 numbers. At most 13 numbers. I will tell you what is the reason I am taking this weird number 13. So if you have at most 13 numbers to be inserted, what I can do is I can go for hashing, mapping like this. So 13 numbers, right? I take an array of 13. So index, let's assume C programming. So my array index starts at 0. 0, 1, 2, 3, 4, 5, in that way, up to I take 7, 8, so on, 9, maybe 10, 11, 12. Okay, this is the array I take. Now your numbers can be anything, right? So how to map them? For that I use modular function. There are a lot of functions available to do this mapping. Generally, one good technique is, take your number, example 277, you would like to store somewhere, but in a fixed location. What is the advantage of getting, what is the advantage you get if you store this 277 in fixed location is, searching will be easy. That is what the main concept of hashing. Okay, so to do that, but we don't have a reserved space for 277. We have only locations from 0 to 12. That's why I use like this. So whatever the number you give, let's call k. Then I do k percentile. What is the size of the array? 13. So this is one hash function we have. Hash function maps our numbers to appropriate memory location here. Okay, so this is called, let's say, bucket. Otherwise, some storage. We have m size storage, right? But the numbers are like anything 1 to n, anything you can store. Then what we do is, whatever the number is given k, so I do k percentile m. That's it. So it will generate numbers between 0 to m minus 1. All are available with me. Correct? So if the number is 2, if this hash, otherwise this is called hash function. If you give a input k, and if I do k percentile m, then I get some remainder. That remainder will be between 0 to m minus 1, right? If that is remainder is 2, then I will store it in this 2. Okay, hash of 2. So I assume that again array name is hash. Then I store it in hash of 2. We'll see a numerical example how this method works. Example, let's say my numbers are 173, 234. Randomly I am picking up. Okay. So 135, 243. How these numbers would go, we will see. First one, 173. So for 173, I do 173 percentile. This is key percentile. What is that hash function? Let's say the 13, right? So if I do this one, this is called hash function. Here, what is the formula of hash function? H of k equal to k percentile 13. Similarly, there are a lot of hash functions available. This is one of the hash function. So it is mapping k to something. What is that something? That we can find out. 173 percentile 13. So 13 1 is 13, 4, 43, 13 3 is 39. You get 4 remainder. The remainder is important for me. So that remainder is going to be the position for storing k. So 173 will be stored in 4. Next 234. Just divide that by 13 first. You get remainder. So 13 1 is 13, 10, 13 8 is 204. Yes, it will be properly divisible. Remainder is 0. So go to 0th location, you write 234. In that way we can store it. Next 135, 13 10 is 130, then remainder is 5. In that way, so elements will be stored. But the only problem you might see here is, what if there are two numbers whose hash function is same? That means both whose hash values are same. Example, 173 is giving 4, right? If I add 173 plus 13, you form a number, you see it will be 186. 186, remainder also same as 173. Let's do that. 186 is in the data, then 186 if I divide by 13, 13 ones are 13, then you get 5, 56, 13 fours are 52, you get remainder 4. Correct? Then it will go again to same position, but it is already occupied by 173. Then how would you resolve? So we have resolving techniques. So this is called collision. Whenever you store 186 and 173 at a time, so you get collision. So to resolve the collision, we have basically two important techniques. One is called chaining. So we are going to see that. Second one is open addressing. Open addressing. So this again open addressing has three models in this open addressing. What is linear probing? Second one, quadratic probing. Third one is double hashing. We'll see one by one.